Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts. Slide 1. Energy in linear magnetic systems, concept and formula. Let's start by understanding what a linear magnetic system is. A linear magnetic system is one where the magnetic flux is directly proportional to the magnetizing force, H. In simple terms, if we increase the magnetic effort, H, the response, flux, increases proportionally. This is similar to stretching a spring. The more force you apply, the more it stretches, in a linear fashion. Now, whenever a magnetic field is set up, especially in coils or inductors, it stores energy. This stored energy is not lost, it's just kept in the magnetic field and can be returned to the circuit when the current stops. The energy stored in such a linear magnetic field is given by the formula. W equals 1/2 multiplied by inductance L multiplied by current I squared. Right pointing arrow W equals 1/2 times L times I square. Let's take a quick example. If L equals 5 henries and current I equals 2 amperes. Then W equals 0.5 times 5 times 2 squared equals 0.5 times 5 times 4 equals 10 joules of magnetic energy stored. We can also express this energy using magnetic field terms. W equals 1/2 multiplied by the integral of B dot H over volume. Right pointing arrow, where B is magnetic flux density, how strong the magnetic field is. H is the magnetizing force, the effort applied. dV is a small volume element over which we calculate energy. This version of the formula is useful when working with field distributions in a magnetic material. Slide 2. Significance of magnetic energy storage. Why is this magnetic energy important? Let's look at its real-life significance. 1. Temporary energy storage. Coils, inductors, store energy and release it when required, especially useful in filters and converters. 2. In transformers, energy is stored momentarily in the magnetic field before transferring between windings. 3. Inductors are designed around this principle and are used in smoothing circuits, filters, and voltage regulation. 4. For example, in DC power supplies, inductors help reduce voltage ripples using stored magnetic energy. 5. When current to a coil is suddenly cut off, the stored magnetic energy returns to the circuit, often causing a voltage spike, which is why flyback diodes are used across inductors. 6. In electric motors and generators, magnetic energy directly gets converted into mechanical energy and vice versa. It's the basic principle of electromechanical energy conversion. 7. Inductors also help in current control, since they oppose sudden changes in current, protecting delicate components. 8. Using magnetic energy wisely improves efficiency in many electronic circuits. 9. Example. In a buck converter circuit, an inductor stores energy during the on period and releases it during the off period to maintain output voltage. Slide 3. Coils connected in series, basics and types. Now let's move to coils in series. Imagine connecting two or more inductors end to end, that's a series connection. In this setup, the same current flows through all inductors because they share a single path. The total inductance depends on whether there is mutual inductance, M, or not. 1. If there's no mutual inductance, i.e., coils are far apart, total inductance is just the sum. L underscore total equals L1 plus L2 plus L2. If there is mutual inductance, coils are close and influence each other magnetically, the formula becomes. For series aiding, L underscore total equals L1 plus L2 plus 2M. Mutual flux helps the total flux. For series opposing, L underscore total equals L1 plus L2 2M. Mutual flux opposes the total flux. 3. Mutual inductance M means one coil's changing magnetic field induces voltage in another nearby coil. 4. In such setups, voltage divides across coils, while current remains the same. 5. Practical use, in filter circuits or inductive coupling where precise inductance is required. 6. Example, two 5H coils in series with 1H mutual inductance aiding each other. L_total equals 5 plus 5 plus 2 times 1 equals 12H. 7. Such combinations are common in power supplies and tuned circuits. Slide 4. Advantages and disadvantages of series coils. Let's look at some advantages first. 1. You can increase total inductance easily by adding more coils. 2. Since current is the same, it's easier to analyze the circuit. 3. Compact circuit design is possible when multiple small inductors are combined. 4. Useful in noise filters, such as ME filters. 5. Helps to control current surges due to increased overall inductance. 6. Placing coils close improves magnetic coupling, important in transformers. 7. Energy can be stored across multiple coils, useful for large power requirements. 8. In high voltage circuits, voltage distribution across coils improves safety. 9. Example, in SMPS, switch mode power supplies, inductors in series are used for voltage regulation. Now, disadvantages. 1. Resistance increases, leading to more energy losses heat. 2. More resistance also causes greater voltage drops. 3. Using many coils makes the system bulky. 4. Magnetic interference might occur if not shielded. 5. Each coil must be rated properly for voltage. 6. If mutual inductance is not controlled, it can distort inductance values. 7. Troubleshooting is harder when more components are added. 8. The cost increases due to more components and space. 9. In shared magnetic paths, core saturation may become a problem. Slide 5. AC excitation in magnetic circuits, Introduction. Now let's understand AC excitation. When an alternating current flows through a coil, it produces an alternating magnetic field in the magnetic core. This results in 1. Eddy current losses. Circulating currents within the core material cause heating. 2. Hysteresis losses, energy lost due to the lag between magnetizing force, H, and flux density, B. 3. According to Faraday's law, a changing magnetic field induces an EMF. A equals negative N times D, dt. 4. If current is sinusoidal, the induced EMF is also sinusoidal. 5. The system's efficiency drops due to core and copper losses. 6. At high frequencies, skin effect forces current to flow only on conductor surfaces. 7. To reduce losses, low-loss materials like silicon steel or ferrites are used. 8. Magnetic cores are often laminated to break eddy current paths. 9. Example, in transformers, AC excitation of the primary winding induces an alternating magnetic field that links to the secondary winding and produces voltage.